Hello students, welcome to EPG Parshala. I am Ashok Goel from the Department of Physics and Astrophysics. Today we are going to discuss about representations of a rotation group from the paper Mathematical Physics. So let us see what we are going to learn in this module. In this module, we will learn about the representations of the group SU2. The group SU2 is of great importance in the study of angular momentum in quantum mechanics. We will also learn in this module about the reduction of the direct product group into irreducible representation of the group. This is also very important in the study of quantum mechanics, particularly in the context of angular momentum for the reducing the sum of angular momenta into the various things which we have already learned. The 2 by 2 unitary matrices, as we have explained earlier, can be parameterized in terms of two complex numbers a and b with the constraint that mod a square plus mod b square is equal to 1 in the form of a 2 by 2 matrix with entries a, b star, minus b and a star. Alternatively, a 2 by 2 unitary matrix can also be written, a most general matrix can be written in terms of, since there are only three real parameters, so in terms of three real parameters theta, alpha and beta, as a 2 by 2 matrix with entries cosine theta exponential I alpha, sine theta exponential I beta, minus sine theta exponential minus I beta, and cos theta exponential minus I alpha. These matrices themselves, first we must realize that these matrices themselves provide a representation of the group SU2. How do we obtain the other representation? We can obtain in fact the other representation by considering the transformation on vectors by these matrices. Let us see how. So consider it in two-dimensional space, consider a transformation from UV, a vector in two-dimensional space, by this SU2 unitary matrix to U prime V prime, such that U prime V prime is obtained from UV by the operation of this matrix A, B star, minus B and A star. Yeah, we are now in a position to construct the representations of the group SU2. A general 2 by 2 unitary matrix can be written in the form of A, B star, minus B and A star, where A and B are complex numbers, with the condition that mod of A square plus mod of B square is equal to 1. Notice that this matrix, the way we have written, has with the constraint that A square plus B square is equal to 1 has three independent parameters. We could also write this 2 by 2 most general unitary matrix in a complex notation as cosine theta e to the power I alpha, sine theta e to the power I beta in the first row, and minus sine theta e to the power I beta and cosine theta e to the power minus I alpha in the second row. Notice that this representation also has three parameters theta, alpha and b. These matrices themselves provide a representation of the group SU2. We can obtain other representations by considering the transformation on a basis vector u and v. Let us consider the transformation u prime v prime is transformed by the matrix a b star minus b a star u v. If we now consider a set of three monomials of the form, now what we do? We have the basis u and v. Now we construct three monomials from these bases, given as phi 1 1 is equal to u square by root 2, phi 1 0 as u multiplied by v, and phi 1 minus 1 as v square by root 2. We will now see how these three monomials transform under the group SU2. So under the group SU2 transformation, let phi 1 1 goes to phi 1 1 prime. which is the equal to 1 by root 2 u prime square. But u prime square is equal to au plus b star v. Therefore, phi 1 1 prime is equal to 1 by root 2 au plus b star v whole square, which is equal to a by root 2 a square u square plus b square v square plus twice a b star uv, which is equal to a square, and u2 square is what? u2 square is root 2 phi 1 1, and v square is equal to phi 1 minus 1 into root 2, and uv is equal to phi 1 0. So expressed in terms of the monomials phi 1 1, phi 1 0, phi 1 minus 1, we can write that phi 1 1 goes to phi 1 1 prime, which is equal to a square phi 1 1 plus root 2 a b star phi 1 0 plus b star square phi 1 minus 1. Likewise, phi 1 0 goes to phi 1 0 prime, which is equal to u prime v prime, and using the transformed u prime v prime, this is equal to minus root 2 ab phi 1 1 plus of minus bb star plus a star a phi 1 0 plus root 2 a star b star phi 1 minus y. The third monomial phi 1 minus 1, which is equal to v square by root 2, is transformed into phi 1 minus 1 prime, which is equal to v prime square by root 2. Substituting for the v prime from the transformation, we find that phi 1 minus 1 prime goes over to b square phi 1 1 minus root 2 a star b phi 1 0 plus a star square phi 1 minus 1. Putting these transformations of monomials phi 1 1, phi 1 0 and phi 1 minus 1 together into the form of 3-column vector with components phi 1 1, phi 1 0, phi 1 minus 1, the transformation then of this can be affected by the matrix, a 3 by 3 matrix, such that phi 1 1, phi 1 0, phi 1 minus 1 prime is given by this 3 by 3 matrix, which can be easily constructed by the transformation which we discussed earlier, operating on the unrotated monomials phi 1 1, phi 1 0, phi 1 prime. So putting all these things together, we can write phi 1 1, phi 1 0, phi 1 minus 1 prime in the forms of a matrix D1 with a function of parameters a and b acting on this column vector phi 1 1, phi 1 0, phi 1 minus 1, where the matrix D1AB can be expressed in terms of the Euler angles. And when it is done so, the matrix of transformation D1 is a function of 3 parameters alpha, beta, gamma, and can be written as a 3 by 3 matrix, which is shown in the slide. Just to emphasize, remember that we have a representation of 2 by 2 unitary matrices in two forms, one in the form of the complex number a and b, with the condition that the sum of this number a square plus b square is equal to 1, and then in the form of the parameters alpha, beta, and theta. So one can relate these parameters a star, b star with the parameters theta, alpha, and beta. So once we have a transformation matrix in terms of the parameters a's and b's, it's easy to translate it in terms of the Euler angle, so in terms of the parameters theta alpha beta or gamma alpha beta. And the transformation matrix then in the Euler angles has the form D1 alpha beta gamma. We have shown the effect of SU2 transformation on the vector UV, on the basis UV, and on the monomials, which are the monomials of degree 2, like U square, V square, and UV. Now, in order to construct representation which are higher than this, we now consider the action of the group on a general monomial of degree 2j, where j can be an integer or half an integer. By defining a general monomial phi jm equal to 1 upon j plus m factorial into j minus m factorial multiplied by u j plus m v to the power j minus m. So you can see that the degree of the monomial phi j m is equal to j because u has the power j plus m, v has the power j minus m, the total power is 2j. The factorials j plus m factorial and j minus m factorial in the denominator have been defined so that we get results which can be easily manipulated. And by defining this phi jm with m varies all the way from minus j to j, minus j in steps of 1. That is, m takes the value minus j plus 1 up to j, such that, for example, if m is equal to minus j, then your monomial is v to the power 2j. And when m is equal to j, then is u to the power 2j. The phi jm then are 2j plus 1 products of u's and v's. These 2j plus 1 functions under the SU2 transformation transform as phi jm prime is equal to 1 upon j plus m factorial j minus m factorial phi jm prime u prime j plus m into v prime j minus m, and u prime is au plus b star v and v prime is minus ba plus a star v. Therefore, phi jm prime can be written as equal to 1 upon j plus m factorial into j minus m factorial under root au plus b star v to the power j plus m minus ba plus a star v to the power j minus 1. Now we can expand the brackets by binomial theorem and we define new indices m prime is equal to j minus k minus l, and then we have 2j minus k minus l is equal to j plus m prime and k plus l is equal to j minus m prime. Making these changes, then phi jm prime can be written in terms of transformation matrix or representation djmm prime as a function of parameters a and b acting on phi jm, where djmm prime function of a and b is given by this expression which is shown in the slide, which is the sum over all k's j plus m factorial j minus m factorial j plus m prime factorial j minus factorial to the power half, and the denominator is a j plus m minus k factorial into k factorial into j minus m prime by k prime factorial into m prime minus m plus k factorial, and with the multiplication a j plus m minus k into a star with j minus m prime minus k b star to the power k and minus b to the power m prime minus m plus k. So all shown in the slide. Having obtained a representation djmm prime in terms of the parameters a, b, we can express the parameters a and b in terms of the Eulerian angles, which is what is usually done. In the literature, the transformation matrix djmm prime as a function of 3 parameters, which are Eulerian angles alpha, beta, gamma, as e to the power minus m prime alpha, small d, j m prime m, multiplied by e to the power minus im gamma, where the small d j m prime m is given by square root of j plus m factorial into j minus m factorial into j plus m prime factorial into j minus m prime factorial, multiplied and summed over the index k of minus 1 to the power j plus m prime minus k divided by k factorial j plus m minus k factorial 1 upon j plus m prime minus k factorial into k minus m prime factorial, and all of this multiplied by cosine beta 2 to the power 2k minus m prime sine beta by 2 to the power 2j minus k plus m prime. The small d j m prime is a function of Eulerian angle beta only, and the full representation matrix capital DJMM prime is a function of the three Eulerian angles alpha, beta, and gamma, which are obtained from this small DJMM prime by multiplying on the left by exponential minus m prime by alpha and on the right by exponential minus m gamma. And in this expression, k is summed over and it takes all integer values such that the factors do not become negative. So now, having obtained the various representation of these matrices, we'll prove some properties of these representation matrices. The first property which I want to discuss is that this representation DJMM prime evaluated for the angles theta, alpha and beta at 0, 0, 0. That is the representation DJMM prime irrespective of the value of j is equal to an identity matrix provided m is equal to m prime. If m is not equal to m prime, this is equal to 0. Now, how do we prove this? So let us say take beta is equal to 0. Now, if you look at the representation DJMM prime, which I have discussed already, the exponent of sine beta by 2 must vanish, or else 5 j m prime m is equal to 0. So the exponent of sine beta by 2 must vanish, means 2k is equal to 2j plus m prime, and which means that j plus m minus k is given by this j plus m minus j minus m by 2 minus m prime by 2, etc. So likewise, j plus m prime minus k is equal to m prime minus m by 2. And this has to be positive. Why this has to be positive? Because this occurs in the factorials and the argument of factorial is positive. The argument of the factorial then implies that m prime is equal to m. Therefore, dj m prime m evaluated at 0 is equal to an identity matrix I with the condition that m is equal to m prime. The other property is that the representation matrix djm prime m for the parameter values alpha, beta, gamma is unitary. To see this, we need to prove that djm prime m alpha, beta, gamma dagger of that is equal to inverse of that. What is inverse? Inverse of the rotation matrix dj alpha, beta, gamma must be the matrix where the inverse means the angles are reverse. So dj dagger of dj dagger must be equal to dj with the sign of the angles reverse. So dj m prime m alpha, beta, gamma dagger is equal to dj m prime m minus alpha minus beta minus gamma. We have to prove this to prove that the matrices are unitary. Notice that dj m prime m alpha, beta, gamma dagger is written as exponential I m gamma dj m prime m beta dagger and exponential I m prime alpha. We will now show that the matrix which is inside dj m prime m beta dagger is equal to dj m prime or minus beta. So to see this, let's put beta is equal to minus beta in the explicit form of the representation matrix djmm prime which we have given earlier. So when we put beta is equal to minus beta, we pick up an extra factor which is minus 1 to the power m plus m prime, and 2j minus 2k is already even. So therefore, there is a overall minus factor. So what are we doing? See, in the explicit form for the representation matrix, when we put beta is equal to minus beta, we first of all we pick up an extra minus 1 to the power m plus m prime. The other factors we pick up are even. Therefore, the net negative factor that we pick up is minus 1 to the power j plus m prime minus k plus m prime, which is equal to minus 1 to the power j plus m minus k, which is equivalent to replacing m by m prime, and beta is equal to minus beta in dj mm prime beta. So the effect is that you replace m by m prime and beta by minus beta in the representation dj mm prime beta. The other property that we discuss is that the representation matrix dj mm prime alpha beta gamma, these representations are irreducible for a given value of j. So that is that these representations are irreducible representation. How will you prove that? We will make use of the Schur's lemma. Suppose there exists a matrix M such that it commutes with the representation matrix. What is the representation matrix? Representation matrix is dj m prime m alpha beta gamma. We assume that there exists a matrix M which commutes with this. That is matrix M into dj m prime m is equal to dj m prime m into m. So what are the possibilities? Let's consider various cases. Let's consider the simple case that alpha is not equal to 0, beta is equal to 0, gamma is equal to 0. Then the only non-zero term that survives is the one for which 2j minus 2k minus m prime is equal to 0, which gives us that phi j m prime m evaluated at 0 is equal to the identity matrix I with delta mm prime, which means that the matrix dj mm prime for all the three angles evaluated at all the three angles equal to 0, that is dj mm prime at 0 0 0 is equal to e to the power minus m prime alpha delta mm prime multiplied by a identity matrix I. And we have also e to the power minus im alpha minus e to the power minus m prime alpha into this matrix M, mm prime is equal to 0. That is, what does it mean? It means that mm prime is equal to 0 if m is not equal to m prime. Otherwise, m is equal to m prime. Which means when m is equal to m prime, which means m is diagonal. Okay. So M is the diagonal matrix which commutes. Further, when alpha, beta, gamma, none of them is equal to 0, we have already shown that M is diagonal. Okay. So we already shown that M is diagonal. So the next thing we want to show is that M matrix multiplied by the matrix D is equal to the matrix D, D, that is M commutes with the representation matrix Dj. Therefore, M of m prime minus m dj m prime m is equal to 0. But for arbitrary alpha, beta, gamma, that is alpha, beta, gamma not equal to 0, therefore we must have the matrix is equal to m matrix m prime m. That is, m is a multiple of identity. So we have proved that if there is a matrix M which commutes with the representation dj alpha, beta, gamma, then for arbitrary values of alpha, beta, gamma not equal to 0, the matrix M must be a multiple of identity. And then by Schul's lemma, it follows that the representation matrix dj m prime m alpha beta gamma is irreducible. Finally, we discuss the character of the representation. The representation matrix dj m prime m of alpha beta gamma is the rotation by fixed angle about an axis. And if we take dj m prime m, then the rotation by a fixed angle about an axis, that forms a class by itself. Since the elements in the rotation group connect one axis with the other, we therefore choose rotation about z-axis by an angle alpha. So what have we seen? We have seen that the rotations by fixed angle about an axis form a class, and elements of a rotation group connect one axis with the other. So we can choose for a class rotation about any axis. So we choose a class with rotation about the z-axis by an angle alpha. Then the character of this class xj alpha beta gamma is the character of the class where we only consider rotation about the z-axis by an amount alpha, because we have seen that the rotations take one axis to another. We can consider only the rotation about one axis, which we, in this case, we have considered the z-axis by an angle alpha. So the character of the representation d alpha beta gamma, which we have represented as chi j alpha beta gamma, is equal to the character of the representation of the matrix of rotation about the z-axis by an amount alpha, which is, by the definition of the character, is the trace of the representation matrix dj alpha 0 0. And from the explicit expression for the matrix dj evaluated and beta and gamma is equal to 0, the trace is simply equal to the sum of e to the power minus im alpha, where m goes from minus j to j, and it is an easy sum, can be seen to be equal to sine j plus half alpha divided by sine alpha by 2. Therefore, the character of the representation dj mm prime by is equal to, for a rotation alpha, the character of this is sine j plus half alpha divided by sine alpha by 2. We will now discuss the product representation of the Lie groups. The product representations are of immense application in physics, and it is very important to know how the direct product of representation resolves into the sum of irreducible representations. For this, let us consider two irreducible representation of the group SU2. Let these two representations be designated by the representation dj1 and dj2. The direct product of this representation dj1 cross dj2, written as the representation d of j1 cross j2, to resolve it into sum of representations, let us take j1 to be greater than j2 without any loss of generality, and let us compute the character of the product. The character of the product is given by chi of the product j1 cross j2 for the group element alpha is the trace of the direct product representation matrices. This trace of dj1 alpha into dj2 alpha, which we have seen earlier is equal to the character of j1 alpha multiplied by the character j2 of alpha. The character of the irreducible representation of the group has been computed earlier, and it is given by sine of j1 plus half alpha divided by sine alpha by 2. Therefore, the character of the direct product representation, namely the character chi j1 cross j2 of alpha is equal to sine of j1 plus half alpha divided by sine alpha by 2 multiplied by sine of j2 plus half alpha sine alpha by 2, where each is the character of the corresponding irreducible representations whose direct product is taken. Now sine A, sine B can be resolved into cosine of A plus B and cosine A minus B. So writing this as chi j1 cos j2 alpha equal to 1 by 2 sine square alpha by 2 cosine of j1 minus j2 alpha minus cosine of j1 plus j2 plus 1 alpha. Thus we have reduced the product which occurs in the character of the product representation as the sum. Now, by adding and subtracting various terms shown in the slides, for example, this chi of j1 cross j2 of alpha can be written as 1 upon 2 sine square alpha by 2 into a difference of two terms, cosine j1 minus j2 alpha minus cosine of j1 minus j2 plus 1 alpha, wherein we have subtracted a term cosine j1 minus j2 plus 1 into alpha. Adding this and subtracting a term cosine j1 minus j2 plus 2, etc., so on and so forth. Continuing this, we can write the character in the form of 1 upon sine alpha by 2 multiplied by sine j1 minus j2 plus half alpha plus sine j1 minus j2 plus 3 half alpha, so on and so forth till we come to j1 plus j2 plus half alpha. This implies that the character of j1 cross j2 alpha is the sum of the characters of chi of j alpha, that is, the character of the product of the representation is the sum of the characters of the representation for a given group element alpha summed over all values of j going from j1 minus j2 magnitude to j1 plus j2 magnitude, which are 2j plus 1 in number. Therefore, from this expression of character, it implies that the direct product representation d j1 j2 of alpha, defined as d j1 alpha into d j2 alpha, can be resolved into a sum of irreducible representations dj alpha, where the sum runs for all values of j from j1 minus j2 to j1 plus j2. Thus, each representation occurs at most once in the reduction of the direct product, and only those irreducible representations are contained in the reduction whose j value satisfy the equality that j is greater than equal to j1 minus j2 magnitude is less than equal to j1 plus j2. For example, if we add two representations corresponding to j1 equal to j2 is equal to 1, then it can be resolved into irreducible representations for the values of j going from 1 minus 1 to 1 plus 1 in the steps of 1. That is, d1 cross d1 is equal to d2 plus d1 plus d0, and so on. Likewise, we can take a product of two representation corresponding to j1 is equal to j2 is equal to half, in which case it can be resolved into two irreducible representations, because j1 half plus j2 half gives us two values of j is equal to 1 and 0. d half into d half is d1 plus d0, and likewise d1 into d half is d3 half plus d half. This is, of course, is familiar to you from the addition of angular momentum, where you know that angular momentum 1 added to the angular momentum 1 can give you a value 2 or 1 or 0. Likewise, addition of two angular momenta or two spins half can give you a spin 1 or a spin 0. So we are now in a position to summarize what we have learned so far in this module. So first thing we have learned is that the rotation by a fixed angle about an axis form a class by itself. And in the reduction of the direct product of representation, each representation whose j values satisfy the inequality that the resultant j, that is sum of j1 and j2, is greater than, it lies between j1 minus j2 modulus to j1 plus j2. And all these representation occur at most once. For example, if we consider two representation with values j is equal to 1 and j is equal to half, then capital J, how many values can capital J take? Capital J can then take values 1 minus half, that is half to 1 plus half, 3 half. So it can take values from 1 half to 3 half only. And all of these representation will occur at most once. Thank you.